In machine learning, we're all chasing that high score, right? A big number usually means we've succeeded. But what if I told you that a model that looks like an absolute genius on the surface could actually be a total, complete failure? Well, today, we're putting on our detective hats to solve the case of the deceptive score. All right, let's just jump straight into the mystery. Is it possible for a model that's 91% accurate to be a complete bust? I mean, that sounds wrong, doesn't it? Impossible, even. But the answer is a resounding yes. And believe me, this uncovers a massive, massive flaw in how we often think about success in AI. Okay, so let's set the scene for our investigation. Our mission, should we choose to accept it, is a real classic in the machine learning world. We're going to teach a computer to recognize handwritten numbers. And trust me, this is the perfect crime scene to show how a really good score can tell a really, really bad story. So our main piece of evidence is the famous MNIS dataset. Now, if you're not familiar, it's this huge collection. We're talking 70,000 tiny images of digits that real people scribble down. For our little case here, we're going to zero in on one very specific job. We want to build a classifier that can look at any of these images and just give us a simple yes or no answer. Is this the number 5, or is it not the number 5? That's it. So we go ahead, we build our model, we run the test, and boom, we get 91% accuracy. I mean, wow, that's an A+ in anyone's book. It seriously looks like we've built a star pupil, a real genius model. So, case closed, right? We can all go home? Well, not so fast. To really understand what's going on with that 91% score, we've got to pop the hood and see what's really happening inside. It's time to find out the secret behind our so-called genius classifier. And here it is. This is it. This is the entire brain, the whole logic behind our 91% accurate model. And it's shockingly simple. Its entire strategy, no matter what image you show it, is to just always guess not a 5. Every single time. It literally never, ever predicts that an image is a 5. So this brings us to the big flashing question, right? If this model is so dumb that its only move is to always guess not a 5, how on earth did it manage to score a 91%? How can something be so fundamentally useless and yet seem so right? Well, the answer, the real culprit, is hiding in the data itself. You see, it turns out that only about 10% of the images in the entire dataset were actually the number 5. The other 90%, they were all the other digits. So by just mindlessly guessing not a 5 every time, our lazy model was right 90% of the time just by default. It correctly identified all the non-5s, sure, but it completely and utterly failed to find a single actual 5. And that is the key takeaway here. Accuracy can be an incredible liar, especially when your data is unbalanced. So clearly, accuracy by itself just isn't cutting it. It's not giving us the whole story. We need a better tool, something that can't be fooled. And that's where the confusion matrix comes in. For this kind of detective work, this thing is your absolute best friend. So what is a confusion matrix? Well, it's basically a way to lay all the cards on the table. It's just a simple grid that sorts every single prediction our model makes into one of 4 buckets. You've got your true positives, that's when it was a 5, and we correctly said it was a 5. Awesome. Then true negatives, it wasn't a 5, and we correctly said it wasn't. Also great. But then you get the mistakes. False positives, that's when we cried wolf, we said it's a 5, but we were wrong. And finally, false negatives. This is when a real 5 slipped right past us and we missed it. With this grid, there is absolutely nowhere for the model's mistakes to hide. So if we apply this to our digit problem, the matrix would show us in plain numbers exactly how many real 5s we actually found, how many we totally missed, and how many times we got confused and pointed at, say, a 3 and called it a 5. It completely replaces that one single misleading accuracy number with the full, unvarnished story of how our model is really performing. And once we have this matrix, we can start asking 2 much, much smarter questions. Honestly, you should think of these as the 2 key interrogation techniques for any classification model you're trying to evaluate. They're called precision and recall. Okay, first up is precision. Think of this one as measuring quality. It asks a really simple question. Of all the times our model pointed a finger and confidently shouted, "Hey, I see a 5," how often was it actually right? So if you have high precision, it means that when your model says it found something, you can pretty much take that to the bank. It's trustworthy. And then you have its partner, recall. If precision is about quality, recall is about quantity. It's about completeness. It asks, of all the actual genuine fives that were hiding out there in our data set, how many of them did our model manage to hunt down and correctly identify? So high recall means your model is a great detective. It's really good at finding all the stuff it's supposed to be looking for. Okay, let's put these two metrics into action and have a little showdown. Check this out. Our dumb classifier, the one that got a 91% accuracy score, its precision is 0, and its recall, also 0. It is completely, utterly useless, and these numbers prove it. Now, let's compare that to an actual smart model. Yeah, its accuracy is a little higher, around 96%, but that's not the real story. The real story is its 93% precision and 82% recall. That's a model that's actually doing its job. So now we have these two really powerful new tools in our belt, precision and recall. And this is where things get super interesting because it leads to a really critical decision. You often have to choose which one is more important. In the real world, what matters more? Is it precision or is it recall? And the answer? Well, it depends entirely on the mission. Let's look at two very different scenarios to see what I mean. First, imagine you're building a content filter for an app like YouTube Kids. Your absolute #1 priority is high precision. You have to be positive that when you say a video is safe for kids, it really truly is. Because the consequence of a false positive, letting one bad video slip through, is just unacceptable. You would much rather have a safe video get blocked by mistake. Now let's flip that on its head. Think about airport security scanners. Here the goal is the complete opposite, high recall. You absolutely cannot miss a potential threat. The consequence of a false negative, letting a weapon go undetected, is catastrophic. It is far better to flag 100 innocent people for extra screening than to miss one single real threat. And this isn't just some philosophical debate. It's a real technical challenge, because there's almost always a trade-off between the two. They're like two ends of a seesaw. If you push precision up, recall tends to go down, and if you crank up the recall, precision often takes a hit. So a huge part of a data scientist's job isn't just to build a model, but to carefully choose that perfect balance point for whatever specific problem they're trying to solve. So I'm going to leave you with this final thought experiment. Let's say you're designing the spam filter for your own email. What do you prioritize? Do you go for high precision or high recall? Just think about it for a second. What's worse, having a few spam emails sneak into your main inbox, or having a super important email, maybe a job offer, or something from your boss, get buried forever in your spam folder? The way you answer that question tells you everything you need to know about why looking beyond that one simple accuracy score is so important.